Welcome back, everyone, to another episode of 26.1 AI Podcast. This is Brian Ray. I'm with my good friend Don Sheu. Today, as our guest, we have Fernando Perez, a Columbia American physicist. He created IPython, associate professor at Berkeley. I approached Fernando outside of a Bloomberg talk Guido gave a couple of years ago. We reminisced a bit about the life of a common friend, John Hunter, creator of Matplotlib. Welcome to a slightly extended commute version of AI Podcasts. Fernando, welcome.
Thanks for having me, Brian. It's a pleasure, and I'm very happy to reconnect after that meeting at Bloomberg. Indeed, it's great to have a chance to kind of reminisce a little bit about John Hunter, who was one of the seminal figures in the world of open source scientific Python from the start. We connected. John and I met back in person at one of the earliest SciPy conferences back when they were held at Caltech, and they were very small workshops. And we ended up becoming both very close professional collaborators in working in IPython and Matplotlib and the rest of the ecosystem early on, teaching a lot together. We taught multiple workshops in the US and abroad. We traveled to Spain, we traveled to India together, taught in multiple places, workshops about scientific Python. We were working on a book together. And we also became very close personal friends. And I'm still close friends with his family, with his widow and daughters. He sadly passed away in 2012, I think that relationship reflects something that to me has been very important in my journey in the scientific Python and open source world, which is the fact that John came from the world of neuroscience. I came originally from physics and applied mathematics, but we combined because of a shared vision of building tools that could be both technically interesting and better, because we both felt that Python gave us a great foundation to build really, really cool tools for scientific research and data analysis and computing, but also that they could be shared openly with the rest of the world for reasons of fairness, for reasons of access, for reasons of reproducibility, for reasons of being truer to the ideals of science, as something where we build a shared vision of reality based on things that we can all work on together and inspect and understand together. And the notion that people came together to collaborate rather than compete, and that out of that, friendships would form, communities would be built that worked together, and that would create new spaces, was something that for me was embodied in John in a really, really strong way. But that obviously goes beyond that, and that has been really a staple of this. John and I ended up being co-founders of the NumFocus nonprofit that supports many open source projects in data science, together with Travis Oliphant, now from Anaconda and Quantsite, who has been your guest in the podcast, with Perry Greenfield from the Space Telescope Institute, the people who basically run the Hubble telescope for NASA, and Jared Millman from UC Berkeley. We had a chance to co-found NumFocus before John passed away. That's kind of a sense in which these original personal relationships and community and shared vision begat larger institutional efforts that I think we all benefit from today. So it's a very good way to weave a connection, and I'm happy to be here. Thanks for having me.
And Fernando, you gave an amazing talk about how you got started with IPython. May I ask you to recount that?
For sure, yes. Thank you for asking, Don. The origins of IPython for me were actually in probably one of the darkest points in my career. I was born and raised in Colombia, and I came to the United States in the 90s to do a PhD in physics at the University of Colorado in Boulder. And I was a graduate student doing my work. And I actually was not doing well towards the end of my PhD. I had a very happy and productive and successful first few years. And then things kind of went south. I ended up making kind of an important mistake, which is something that now I try to convey to my students, in that they should be very careful in who they choose as a mentor, and that they should choose mentors not only for their intellectual qualities, but also for their human qualities, for the kind of behavior that they exhibit towards especially towards their more junior people, towards their trainees. And I chose, unfortunately, a PhD advisor who was an extraordinarily talented theoretical physicist, but an extremely toxic individual. Long story short, this fellow fired me. He actually fired me on my 5th year of grad school. Just to be clear, being a foreign student in the US on a foreign student visa and being fired from your PhD on your 5th year is about as close to a completely career-ending disaster as you can have, because without the PhD program, I don't have a visa. I have to get out. I'd have to go back to Colombia with nothing to show for 5 years of work. You can imagine that it's a pretty bleak picture. I was rescued by a wonderful Hungarian physicist, a woman named Anna Hasenfratz, who was my professor, a colleague of this other person, and she was both brilliant. In fact, she was the person that I originally wanted to work with, but she didn't have funding early on, and I ended up working with this other person. But she basically rescued me at the end to finish a PhD through a project that I was helping her with. And in that process, we did have to do a lot of sort of lightweight interactive data analysis and modeling. And most of the workflow we had was based on Perl. So I had written a lot of code in Perl at the time. I had written a little bit of some open source tools in Perl. And I used it for wrangling, loading data files from simulations, feeding them to plotting packages, feeding them to analysis packages. And my office mate told me, look, there's this Python language out there that's kind of like Perl, but nicer. And you can actually use it interactively. And I was very used to interactive environments like Maple and Mathematica and IDL, where you can type a little bit of code, look at an answer, maybe plot some data, and iteratively construct an answer by using the computer as a thinking partner. Python had an interactive shell, but it was very primitive. And what happened was I started reading the Python tutorial, and in 24 hours, I started knowing how to do things in Python that it's not just that I didn't know how to do them in Perl. I didn't know if they could be solved in Perl. I didn't know if they were doable in Perl. And the Python object model, the Python data structures, the Python syntax was so clean and so coherently organized that I was able to very rapidly devise really cool solutions. And I totally fell in love. And connecting it back to this other part of the story, which is that I was pretty desperate and in a pretty dark point in my career, I got sucked in and I fell in love, and I said to my advisor, you know what? I think I can do this. I'm going to do this little thing for an afternoon that I think will be useful. I'll get back to you tomorrow. I spent about 6 weeks. I kind of disappeared from her radar. She was kind enough not to fire me a second time. And I went down a black hole of just coding like a maniac for a few weeks. Importantly, from the beginning in a collaborative fashion. So I started writing what became IPython, but I discovered 2 other projects out there to do also interactive Python that had ideas that I was already thinking about, but they had already implemented some of that. One was a project called Lazy Python by a grad student at Caltech, and the other one was a project called IPP, Interactive Python Prompt, by an oceanographer in Germany, in Hamburg, I believe. Janko Hauser was the German, and Nathan Gray was the grad student at Caltech. And I emailed both, and I told them both, look, guys, you have these 2 tools, and I have this IPython thing that I started writing. They're kind of similar. How about we combine forces and we build something together? And interestingly, they both gave me more or less word-for-word identical responses. Great, go for it. Use my code. I'm way too busy right now with other stuff. Just take it and do whatever you want with it. And being in a position of wanting to escape from my PhD disaster, I merged the 3 code bases, wrangled them together with a lot of duct tape and bubblegum wrappers, and thus was born the first IPython that I posted to the Python mailing list and the SciPy mailing lists in December of 2001. And importantly, what that gave me was confidence, right? I mean, the reason why I told this story about my little personal disaster is because writing code, writing IPython, finding others who wanted to work with me, these other 2 people who I had never met, I emailed them out of the blue, who both were willing to work with me, gave me confidence back. And when I posted IPython to the Python Lang mailing list, the Python mailing list, and the SciPy mailing list, which was nascent at the time, a tiny community, people immediately said, oh, this is great, this is useful, thank you for sharing it. How about this other idea? That sense of feedback basically gave me energy and motivation back to say, you know what? I may be in trouble with a physics theoretical physics PhD, but I can do something useful. I'm not useless. I can code. I can do something that'll be useful for science. And that got me out of that dark hole. Eventually, a few months later, I actually said to everyone, okay, I'm not coding in this Python thing anymore. I've got to graduate. I've got to finish that thesis. In fact, when John Hunter sent me the first patch, his first kind of matplotlib type code was a patch to IPython to support a different plotting syntax, because IPython, I added some plotting support to it. And I told John, look, I'm in the middle of finishing my dissertation. I promised my wife, my therapist, my advisor, my parents that I would graduate. I really can't look at this right now. So John went off and said, well, I guess I'm going to have to do Matplotlib on my own. And he started a separate project. We became very close friends a year later, but at the time I was trying to finish. But the point I'm trying to make is that there was a combination of collaboration and practicality that gave me a road forward from day one, and where this notion of a collaborative community was really critical from the very beginning. I was invited by Eric Jones, the founder of Nthought, to the SciPy workshop in 2002. And he said, if you can't make it, I'll fly you, I'll cover your costs, just come on over. That's where I met John Hunter, I met Travis Oliphant, I met Eric, I met many of the people from this community, and discovered that all of us wanted to work in a similar spirit to build these tools. And we all thought that both Python was a good technical foundation, and the collaborative process was a viable one to build something superior to the proprietary tools. And off I went. And obviously, what we've done, what is today Jupyter and the rest of IPython, is not my work. It's not only was it collaborative from the beginning, many other people have come and have made what we have today possible. But I want to flag that from the start, there was this kind of sense and spirit of collaboration, both in my interactions with the people who contributed to the seeds of IPython, and people from the community who supported me, like Eric and Travis, and in people like John, who were collaborators who became immediately friends and kind of creative forces in this space.
There's no secret that the contributions that you started there in the community was out of necessity and turned into something big. Fast forward now, many years later, you see this Jupyter notebooks everywhere. It's become common nomenclature in the data science world. How do you feel about that? Do you feel the same sense of collaboration is there? And what sort of problems do you see solved with this?
So I think we've learned a lot. We've learned a lot. I mean, on the one hand, I am incredibly excited and fundamentally grateful to both others who have contributed, the people we have worked with, my co-director in the project, Brian Granger, with whom I've worked extremely closely for the last few years, all of the people who have built the code and the community. So it's incredibly rewarding to see that something that began as an act of desperation, and where multiple people told me I shouldn't do it, because people in the more traditional academic world that I was a part of did actually tell me, stop doing this. This is a waste of your time. This is a bad use of your talent. You need to go back to physics and mathematics. That's what you're good for. Just go back to writing papers, basically. For some reason, I didn't listen, and I think it was the right thing to do, but it was hard at the time to tell my bosses and senior mentors that I would not heed their advice that they felt was the most important advice they were giving me. But over time, what we've learned is that the code is only a small part of this whole story, right? And that's years later, we had to write down formal governance machinery for our projects. We then had to get fiscal support. When we founded NumFocus, one of the first things we did was develop the framework for fiscal management so that we could accept some funding. For example, at the beginning, Microsoft offered us some financial resources for IPython. It was still before we had the Jupyter name. And at the time, we had no way of even accepting a donation, right? And so how do we do that? Well, you need the proper legal structure. And that requires a community of people with different skills. It requires solving problems beyond just the technical issues of the code. And so what we've learned, and today, sometimes I use a little bit of a like Maslow hierarchy of needs style pyramid diagram, where the tip of that pyramid for an open source project like Jupyter is actually not the software itself. The tip is the content that and the stories that people build with the tool. Because for many people, the tool powers something towards the goal that they have. They want to write a paper. They want to develop software, their own software. They want to build a website based on their analysis. They want to build a product for their clients. They need to build a report for their bosses, etc. Right? It is the story around the problem they're understanding, the analysis they're doing. That's what they need to convey. And what we found is that by making tools like the notebook viewer, NB viewer, that made it possible for someone to share a viewable link to a notebook with one click, and then share that on Twitter, on Facebook, on GitHub, and social media, etc. That became extremely important, because what people were able to do then was tell the story about their data, their problem, not just talk about software, right? So offering people services where they can convey their own content, Binder, NB Viewer, Jupyter Hubs that can be deployed anywhere, is actually probably more important than the software itself for many people who just view it as a tool, and rightly so. Now, below the software, there's an important layer that we've taken a lot of time to develop in Jupyter, which is the layer of expressing the ideas of the software as open standards. And so in Jupyter, for example, we took the time to document how does Jupyter communicate with the IPython kernel, what kinds of messages does it send over the wire, what kind of data is encoded, and all of that is documented in formal documents. There's libraries that implement it, there's test suites to validate it, and the point of doing that is that it allows the Julia team to build a Julia kernel in pure Julia without using any of our code. It allows the QuantStack team in France to build a C++ interactive kernel purely in C++ that implements the protocol without using our tools. The point is, by expressing the ideas behind those tools as open standards and open protocols, we then support an ecosystem of interoperable tools, rather than simply saying, well, here's something for free that you can use, but you have to stay within our walled garden. We actually want others to build on not just on the use of our software, which obviously we're happy to see, but also on the ideas that we've captured, because sometimes others may build new things that are different from what our software offers, but still be interoperable. And then there's a fourth layer at the bottom, which is the human community. And that human community requires governance, it requires management, it requires support, it requires attention to issues of conduct, of diversity, of communications, of trademarks, of many other things that are not necessarily purely on the software and technical sides, and that are just as critical. And we've learned a lot about that. We've made many mistakes along the way. We're currently in a new iteration of our governance model to basically continue scaling to the size and scope that we have. But the development of that understanding, if you had asked me 20 years ago, I would have thought it's all about the software, right? And today, I see this bigger picture as something that is challenging, but also fascinating. And ultimately, that is what makes a project like this something that can have a much larger impact than something which is just the code, right? It is the fact that there's a story to be told, there's ideas to be captured that allow a broader ecosystem to grow, and there's an entire human community around it that goes beyond what any of us individuals could do.
You've been breaking down walls around gardens here, and now how does it feel to have to find room for 1,200 students for your data science course?
Well, so we're talking about Data 100, the course for which I gave today, this morning, the closing lecture, and I think we've already put it up on YouTube. So I'm happy to share a link if you want to include it. If folks want to take a quick peek at what we do in these large lectures, it's a fascinating challenge. The physical challenge, obviously, is how do you squeeze 1,200 students into a room on campus? The answer is we can't anymore because we don't have a room where we can, a lecture hall that fits, the biggest one fits about 750. And so we have to go digital. This year, obviously, we went digital for everybody. But to me, it's incredibly rewarding to realize that by having built all of this open source stack, now we get to teach something like this is possible. We can bring 1,200 students, put them in front of a Jupyter Hub instance that is managed by campus, that runs in the cloud. We are not doing tech support for 1,200 students. It would be completely unthinkable to solve installation issues and configuration issues and whatnot across 1,200 people, right? With all kinds of different like laptops and hardware and whatnot, operating systems, et cetera. And instead, we can give them infrastructure that is 100% free, 100% under the control for privacy reasons, for many reasons of the university. But that is not a toy, right? These students are now learning with Jupyter, with NumPy, with Pandas, with Matplotlib, with scikit-learn, with scikit-image, etc. They are learning with the exact same tool stack that they will use in research, in industry, at companies, in a PhD, in a job for a client, when they go out into the real world, and they're doing it analyzing data, real world data in the cloud. We're not giving them just a toy data set that they can copy into Excel on their laptop. They're working in the cloud with real world data sets. And being able to do that is a dream that I had since I was in college. When I finished my undergrad in Columbia, right before coming to grad school, I actually taught a course in computational physics for undergrads in my department in Columbia. And that course, we jury-rigged a complicated solution using GNU plot and C with old terminals from a VAX into a Linux machine that somebody configured. Long story short, it was a disaster because the tech was clunky and complicated. Most people didn't. My students didn't know how to program in C. So of all my students, only one managed to actually be able to get through the technical barriers to think about the physics and the algorithms. And I remember telling myself, I never want to do this again. The next time I teach something like this, I want to do it in an environment where the students can sit down, and from day one, we can focus on whatever matters for that course. It's perfectly okay to struggle with pointers and memory management in C if you're teaching a course in C programming for people who need that at a low level. But that wasn't my case at the time. And so what I said was, I want to be in an environment where what I'm teaching is physics, data analysis, et cetera, then that's what we can do from day one, from the start. And the students can focus on the thinking, on their data, on visualizing, on understanding the phenomena, et cetera. The problem was 20 years ago, that environment didn't exist, and it certainly wasn't free, which in Colombia, using proprietary expensive tools would have been a non-starter. And it's absolutely wonderful to be able to see that now we have those tools and we can do it, and we do it at scale, and we do it successfully. And we're doing it with the same tools that the Event Horizon Telescope team is using to make the first image of a black hole, that the LIGO team used 3 years ago to make the first observation of gravitational waves that led to the 2017 Nobel Prize in Physics, right? As a physicist, for me, it is unbelievably rewarding to realize that this ecosystem of tools that we built powers those discoveries, but it's the same stuff that I can then turn around and bring to my students and get 1,200 of them learning how to properly analyze and model a data set. So breaking down those walls is extraordinarily rewarding.
Do you see an impact of the outside world to solving some of these problems that are being solved with some of this technology today, whether it be viruses or climate or anything like that?
Absolutely. And I mean, I'm sure that historians of science will have a field day over the next, or field years over the next few years, disentangling when the dust settles and people can catch their breath and get some sleep on what happened with the COVID process. But I am sure that there will be places in that process where we will have identified that some of the scientists were able to advance faster, to collaborate, to work together, because we had cloud tools, because we had openly available data. I do know, for example, that the very first sequence of the viral genome that was published back very early in the pandemic made its way out from China, from some scientists who put it up online, and that, for example, some of the scientists at Pfizer and at the German biotech startup that they were collaborating with apparently had that sequence. They grabbed it, and literally within, my understanding is, and this I'm quoting from an article in the New York Times recently, that they effectively had the sequence for the vaccine within 48 hours. Basically, they had done enough research, they had enough machinery that knowing the viral vaccine, the viral genome sequence, they had a pretty reasonable sketch of the vaccine sequence within 2 days. Now, obviously, having the vaccine sequence in a computer is not the same thing as having a vaccine that's been tested in humans. That took a year, but even a year for that is a remarkably fast turnaround. And one that probably would not have been thinkable 20 years ago if people didn't have the ability to do something like this, which is some Chinese scientists have the virus in their lab, they go ahead and they sequence it, they post it online. Immediately, folks are somewhere else who have some of the other machinery ready and deployed, grab that. It's just a file. It's just data. They load it into their pipelines, and within 48 hours, they've been able to do the modeling and design for what should be the genetic sequence of the new mRNA vaccine. That would not have been conceivable 20 years ago. With climate change, I'm glad you're asking that question. I think it's the existential threat of humanity today. And a lot of my work today is actually around that. So I've most of my funded work right now is on a project called Jupiter Meets the Earth, which is basically Jupiter combining the work we're doing in Jupiter with research in geosciences and climate change, precisely to build technologies and tools for that for those problems. There's a lovely project led out of Columbia University and NCAR called PanGeo that takes Jupiter, Dask for distributed computing, XArray for large-scale data set management, and related tools in the scientific Python ecosystem, and assembles them to basically build cloud platforms for doing very large-scale data analysis for geosciences. It turns out that in the geosciences, the data has outpaced what individual scientists can manage. To give you a very concrete example, the data for comparing and validating climate models, that's a very large international effort that happens every few years. It's called the CMIP project, the Climate Model Intercomparison Project. The data for the current edition of CMIP, which is called CMIP 6, is on the order of 15 to 30 petabytes. 30 petabytes is not data that anyone is going to download ever anywhere, right? It doesn't fit on any one computer. The only way to operate with that data is to put it somewhere and bring people to that data, right? The analogy that I like to use for that is the watering hole. Like a watering hole in the African savanna is a place where many species, some of them who are predators of one another, come together because they all need the water. And this little ecosystem, semi-cooperative ecosystem grows there. Well, we have the scientific equivalent of a digital watering hole now, which is data, open data in the cloud, combined with the scalability of the cloud to deploy compute resources elastically and flexibly. If you put open source tools on top, allows communities to come and form who can understand that data. Because the other aspect of this is that the sheer size of complexity of that data doesn't only mean that you need big resources, you also need big teams. No single individual can make sense of that. The skills needed are complementary. The data that we need to understand for problems like climate change is data that has multiple aspects and layers. You need people who know about numerical models. You need people who know about atmospheric physics, about atmospheric chemistry, about soil chemistry, about microbial ecology, about social and economic impacts. Well, all those people can come together if the data is open, if the cloud infrastructure is openly available, then those communities can form and we can begin to build together, hopefully, a shared understanding of the problem, a shared understanding of the optimal solutions. And by making those data available in the cloud and the conclusions that we draw from there visible, dashboards that are available to policymakers. Rather than passing PowerPoints around, we can share not just NB viewer links, but we can share live dashboards that operate against the real data so that we can explore solutions, scenarios, etc. And so we can connect these communities of understanding from the scientific side to communities of decision making with policymakers and the general public that hopefully give us solutions. So I'm not claiming that we're going to magically solve a problem as complex as climate change, but at least I do hope that by working in this spirit and with these tools, we are making a positive contribution.
Obviously, positive contributions. And to put it on a more personal scale, I mean, you do an astonishing number of things, and let's put it that way. What do you wake up so motivated in the morning to do? What drives you personally?
Right now, it is precisely the combination of continuing to build this open source ecosystem in a healthy and sustainable way with this vision of bringing data and computation to the world in an open fashion to tackle these problems together with this topic. So I have narrowed the scope from a topical perspective of my research precisely into Earth and climate. A lot of my work right now is actually even within the sphere of geosciences and climate change. I'm very interested in understanding the fate of ice on Earth. So I actually have from a technical perspective, some of my research is now specifically in collaborating with what are called cryosphere scientists. So my training was in particle physics, very theoretical, but I've basically hooked up with really talented geophysicists and cryo scientists who work on that on that problem. And we're trying to basically build these tools in that specific space. But at the same time, I'm trying to continue. So I like to have a driving problem that motivates me and that gives me a concrete use case for me to explore with my students and colleagues and postdocs and whatnot. But I'm also continuing to build kind of the vision. And the next step in that is actually something that we just launched publicly a few weeks ago. Our first kind of very publicly visible launch was a talk that we presented at the JupyterCon a few weeks ago, and it's an initiative called 2I2C, the International Interactive Computing International Collaborative. And this is an effort founded by a team that includes a person from one of the leads of the Pangeo project I just mentioned, Ryan Abernathy. He's a professor at Columbia University, a mathematician at the University of British Columbia, Jim Colliander, who directs an institute in Canada at UBC, and who started providing Jupyter hubs to Canadian researchers and educators, all the way ranging from K through 12, all the way up to supercomputing resources, and a team of five folks from Berkeley. Catherine Carson, a professor in history, Lindsay Hagee, who is a postdoc of mine in geophysics, who actually will be faculty at UBC soon. Chris Holdgraf, who's a neuroscientist from Berkeley, who was a postdoc and now will be a director of the 2I2C initiative, and Yuvi Panda, who is a brilliant software engineer from Berkeley who supports a lot of the Jupyter hubs that we use for education and who's one of the lead developers of Jupyter Hub and Binder. So with this team, what we did was we started an initiative to try to both offer Jupyter Hub and related deployments using open source infrastructure for researchers and education, basically the kinds of things that we can do at Berkeley for these very large classes, the kinds of things that Pangeo does for scientists, the kinds of things that Jim Colliander had done in Canada for Canadian researchers and educators, but being able to offer that as a service for pay, with contracts, with SLAs, et cetera, but simultaneously doing it with a nonprofit mission that is centered on the needs of scientists and the needs of educators, and with a mission to contribute back revenue and resources to the open source development. Because as much as I love collaborating with industry, and we have great relationships with Bloomberg, with Amazon, with Microsoft, with Google, with IBM, with many of the leading tech companies, and I'm very happy that they use our tools, I think it's important that the purely neutral, nonprofit, open source scientific and education community also has a voice. And so we founded this nonprofit entity. It is housed under the fiscal umbrella of the International Computer Science Institute, which is a research institute at Berkeley. But we are not a Berkeley entity. We have this international collaborative team who hopefully will build both services that are needed and that universities want to have, but they don't quite have the right staff, and no one is offering them exactly the right offering. And simultaneously, we will gain sustainability and basically a financial stream to have staff that can do that work while contributing back to the open source project. So that's kind of one big initiative. So to summarize, one line of work is kind of the technical work on Jupyter and geosciences for climate. And the other big line is this notion that we need to create an entity such as this one that didn't quite exist, and that for years I struggled with what was the right approach. And I'm very excited to be building this one.
I love it. I think it's great. And I was going to ask the question about the hyperscalers and using your software, essentially the open source software that's really driving a lot of industry innovation, how you felt about that. But I think you answered that, that they're also contributing back, and they should be, to some of these open source efforts. Is that true?
Yeah, I mean, it's a complex relationship. It's a very complex, and I'm not the first one from the open source world. There have been very, very loud and vocal blog posts and arguments about this issue in recent, especially in the last year or so. I've seen some really thoughtful posts from folks in the open source community, because it is a challenging situation. There is a bit of a tragedy of the commons issue here. Some companies do contribute, and they do contribute well, and we've had wonderful collaborative relationships with multiple companies, and we're very grateful for that. But that's not true of all. And those contributions are uneven. And the problem is also that we don't have a good mechanism for those contributions to be sort of steady and fair. I am convinced that industry, even though some companies, and there are some folks at these companies that do a wonderful work, I would say that at large, industry is definitely getting more for free from the open source world than it is putting back in. And I think that's unfortunately, it's understandable why the mechanisms of that happen, but it is short-sighted. It is a classic tragedy of the commons issue. Any one company can act in its best self-interest by taking what it wants for free. But when they all do that, nobody is sustaining that ecosystem in a way that keeps it healthy, that keeps people employed, that allows those projects to continue building, to continue innovating. And many companies see both the software and the people building it as simply resources to be plundered. For example, oh, great, this is a great team, let's just hire them. They're going to be great engineers, but they hire them and they disappear from the public world, from making public contributions. That has happened over and over. I mean, people end up with a nice career, a good, well-paying job, but the world loses something. Or they simply take the software, they put demands, they ask for bug fixes, etc., and they don't contribute back, and the maintainers burn out, and they may just go and do something else. We've seen instances of all of that. And so I maintain that it's a good thing to have industry participation, and that it's great that industry uses these tools. We wouldn't be where we are without industrial use, and they also bring a lot of use cases, needs, and resources. But the relationship is not a perfect one, and we continue to explore that. Our creation of 2i2c.org was, in a sense, an attempt to provide one more potential solution. This is not a problem that will be solved by any single answer. So 2i2c.org is an attempt to bring another player with a different set of constraints and motivations to help with this question of sustainability.
And you're solving real problems with that organization, and it's going to impact the globe. Do people realize or understand the negative or positive, in this case, impacts of data science and machine learning? Do people get it?
I think some people do. I think we have at Berkeley, for example, our data science major, our data science division has a large section of it called Human Context and Ethics, with mandatory courses with scholars who study these problems at the intersection of computation, social science, ethics. Right, Catherine Carson, my colleague, she's a professor from the history department. She comes from the world of history of science, but she's been the person basically leading the intellectual charge on the creation of this human context and ethics part of the division of data sciences. We have scholars who work in that field. Obviously, not just at Berkeley. I happen to know my colleagues better than others, right? But I think there are a number of places and a number of scholars who take this extremely seriously. I think this year I've seen an elevation in the quality of that debate, in the sense that I think a number of scholars have really come out with very compelling demonstrations of some of the truly harmful impacts of the bias that can come out, racial bias, gender bias, social bias that can come out from the way machine learning systems are engineered and deployed in the real world. It is disheartening, though, to see that some of those leaders are actually being not treated probably in the best way that we would expect. You may have seen that right now there's a big brouhaha. The dust hasn't settled, so I'm not qualified enough to speak as to what exactly happened. But one of the leads from the Google ethical AI team, Timnit Gerbu, who is a brilliant Ethiopian scholar in the field, and who co-led that team at Google, was very vocally fired, apparently, by the Google ethics and AI team, precisely for speaking up about issues of ethics in AI and with issues that affect the Black community in AI. And that is concerning. Seeing a company like Google handle one of their leads in that space, one of the most respected voices in the space, a Black woman who has been an intellectual and community leader, both in both aspects in this space, handle it that way is worrisome. As I said, I don't have all the facts, but I know as much as you may know from just reading the news reports about it. But it's certainly something that I find incredibly concerning, that this is happening to the people who have led the charge in pointing out that this is complicated. There's legitimate issues that we need to address and that are uncomfortable. Folks like Timnit Gerbu have pointed out things that people don't want to hear. And we should listen to those voices, respect them, and give them a space rather than silencing them. So do people get it, was your original answer? Some people do. I hope more people do.
And you already answered. I always ask the precautionary tale, and I think you just told it to me. So I don't need to ask that question, but I always ask that. On kind of one final topic is, I mean, you have literally thousands of students that pass through your classes and whatnot, and this is a hot field, obviously. For those who are talented and those who have the ambition to make change and be successful, what advice would you give them to be successful in this space? Is there any trick to, I mean, you've been successful, I believe I have as well. And what advice should we give them?
Oh, I mean, I don't think that definitely my career has been the weirdest, most convoluted, zigzagging, backtracking path imaginable. So following me is not a good idea. And it came very close to not working out many, many times. What I would suggest to my students is a combination of, first of all, solid foundations, right? Data science is still grounded on important technical ideas around computation, around linear algebra, around statistical inference. Getting a solid understanding of the foundations, that is capital that you get that gives you payoffs many times over the years. So not skimping on the foundations is important, and especially on understanding, at least, you don't need to have written every line of code of every tool you use, but you need to understand what assumptions tools make so that when you use the tool, you know its limitations and you understand it. Because the tools are very powerful, but they can look more powerful than they actually are. Just because your tool spits out a confidence interval doesn't mean that confidence interval makes sense if you don't know how it was computed, if you don't know how the samples it uses were obtained, et cetera, et cetera. So it is important that you have the foundations right. The second point is interest in a domain. Domain knowledge matters a lot. And the data is not some abstract entity that has some platonic pure perfection. It is dirty, and the dirtiness comes from where the domain, where the data is drawn from. And you can only make sense of the dirtiness and distinguish what dirt is useful versus what dirt you need to wash away if you understand a little bit of the domain. So I always tell my students, go find something where you care about the topic, where you care about the answer, so that you actually can combine that foundational knowledge with meaningful steps that you take through as you make your way through the problem, rather than blindly sort of, I have a hammer, everything is going to look like a nail, and I'm just going to pound on everything that crosses my field of view. And then lastly, going back to this aspect of ethical and human and social impacts, is have that always in the back of your mind, or not in the back, in the front of your mind, which is, as you build your systems, as you make decisions, as your models spit out predictions based on which you will make a decision, ask yourself, who is going to be impacted? In what position are they? Who collected the data that you're using to feed that model? What position, what biases did they have? Not because bias is not bad. Bias is a property of the world. Limited systems make decisions with limited information. Therefore, they have bias. So it's not about eliminating bias. It's about understanding what biases you have so you can appropriately control for them, correct them, perhaps compensate them. Perhaps you can average them out. You can't eliminate them, but you can perhaps average them out by coming at the problem from a different angle. But you need to ask those questions throughout the process. So I would say those three pillars, sort of the technical grounding, the human grounding, and the domain, are all equally important.
That's the best answer ever, and I really appreciate it. I'd like to dedicate this episode to John Hunter, and I want to thank you very much, Fernando, for taking the time and speaking with us today. I think it was a great episode, and I can't wait to publish it.
Thank you both, Brian and Don. I greatly appreciate the opportunity, and I couldn't be happier than closing with this dedication that I fully second to John. John was truly like a brother to me. He was a visionary in this space. We owe him a lot because a lot of the viability of the open source scientific Python ecosystem actually came from work he did early on, back when it was just a glimmer in our eyes. And I'm very sad to have lost such an incredible person, but I'm very happy to honor his memory today. Thank you.
Well, great legacies live on. Thanks again,